Right, we now move to magnetic fields around straight conductors. We have been studying magnetism as a physical phenomenon caused by the motion of electric charges. But when you have been studying it so far, you've been looking mostly at magnetism caused by bar magnets. So you have been drawing the magnetic field between the north pole and the south pole of a bar magnet, and we know that it has a specific shape, and that shape is this curved, oops, I'll go around here, that curved shape. That these are vector field lines, and they go from north to south, and the direction of these field lines are always pointing away from a north and towards the south. The phenomenon of magnetism done by bar magnets is ferromagnetism, and we have magnetized this iron here by aligning its domains, and you've previously been looking at the domain theory of magnetism. But the domains themselves are created by moving electric charges. The atom itself, the iron atoms and the electrons associated with them themselves create the magnetism. So magnetism is created as a phenomenon by the motion of moving electric charges. So apart from bar magnets, where else do we find magnetism? Well, we know that around a straight conductor, I'll move to this slide, we have a magnetic field, and this was discovered by a fellow by the name of Ørsted. And he found out that around a straight conductor carrying a magnetic field, carrying a current here, there is a magnetic field. And the strength of that magnetic field is determined by Amperes Law. So in this formula here, which we'll go through first before we go around and look at the magnetic field around the conductor, B is the universal symbol for the magnetic field strength. And the magnetic field strength its units are Tesla. Nicholas Tesla, and the symbol is capital T. So the actual symbol for magnetic field strength is B, and its units are T. I is the current, and we know that current is in amperes, after whom this law is created, and R down here, which is the other variable in this equation here, is the radius of the field, which we're going to say is the distance from the straight conductor. So this law is used to determine the field strength. Determine the field strength. That's the magnetic field strength at a certain distance away from a line. And that line is the wire, and that wire is carrying a current. Now remember, current is moving charges. Current is the amount of charge per second moving down a wire, down a conductor, and therefore we have moving charge. Moving charges create magnetic fields. You'll notice that there are two other symbols in this law. Obviously we recognize pi here, and that is the normal pi, so that's the other constant, but this one up here is new to us, and this one up here is going to be, well, it's not going to be, is the permeability of free space. Not to be confused with its cousin over in the electric section, which is the permittivity of free space. The permeability of free space is a measure of how well the magnetic field can penetrate a vacuum or the substance that it's moving through. And our values for this are 1.257. I'll write it down here, so it's 257 by 10 to the minus 6 newtons per amp squared. Now, we're not worrying too much about its units, but the value that we'll be using in a few more moments is 1.257 by 10 to the minus 6. So it's quite a small quantity. Okay. Right, let's now move to using this equation. And here we have two diagrams of a conductor, and it's carrying a current. And so we'll have one which is going horizontally at the moment. And as a result of this conductor, we're going to be trying to work out that what is the nature of the magnetic field around this conductor. Now, according to to Ørsted, that if a current wire in this direction, then we can determine the shape of this magnetic field as concentric circles around this wire. So I'll just do it try and do it in a 3-dimension for you. I mightn't be too successful at drawing this. So here is the wire. And around this wire, with the current going in this direction, there is a whole series of magnetic fields which are concentric circles. So I'll try and do it here. Like that. And these are the field lines going around. And obviously there's a whole series of them. So there's a bigger one up here and a bigger one there. And these are concentric circles around the wire. And it becomes really confusing to draw it that way. So what we're going to be doing is we're going to use dots and crosses. A dot is going to be where the field is directed into the page, out of the page, I should say. Okay, and a cross means directed into page. Okay, so now doing the 3 dimensions is really hard to look at. There's a few examples online and in your books to have a look at the 3-dimensional picture of it. But we're going to use the right-hand grip rule for straight conductors. So using your right hand, here is a thumb of the right hand. There's a thumb. Okay, that's a very bad thumb. I'll try another one. So here's our thumb. Okay, there's my right hand. Then you just relax your fingers into like a grip. So I have there's our, I think the thumbnail's on that end, not the other one. That's it. And there's your fingernails. Okay. Now your thumb points in the direction of the current. And your fingers wrap in the direction of the magnetic field. So this is a concentric field, a concentric circular field that is coming out of the board above. So it's coming out from up here. So I'll put 4 dots in to say it's coming out. Okay. We're only going to draw 4 field lines. And it's a circle, so it's going out and it's coming in on the other side. So you need to recognize or imagine half a loop from this point to this point. And then the other half of the loop goes behind the board, behind the screen, and back up. There is a whole series of these dots coming out of the board on this side and into the board on this side. Out of the board, into the board. Out of the board, into the board. Out of the board, and into the board. Let's remove these away from our things here. And the formula that we are using is B is equal to a constant. Now this constant is mu naught on 2 pi times I on R. So B is proportional to 1 on R. So as we get further and further away, the field strength is going to get less and less and less field strength. So the field is going to be strong here, in this area here, close to the wire, and it's going to weaken dramatically as you get further and further away. So looking at it top on, so let's now try and draw it in a looking with your eye. Here is your eye, there's your eyelashes and your nose. You're looking directly at that wire. The wire would look like a cylinder, very long, thin cylinder, and you would see the current coming towards you. Now, something coming out of the board or towards you is a dot. We always represent a dot as coming towards you and a cross going away from you. And around that wire, there is a circular magnetic field. So we're going like that. So these circles, like this. Now there, so your eye would see the circles getting bigger, like that. So your eye is seeing these field side on. And the direction of that field will be coming out of the board and going into the board on this side. So it'll be out from here and into there. Out from here into there. Okay. Once again, you use your thumb and your grip. So looking at your thumb, so looking at this edge on. So you're putting your thumb pointing to your eye. You would see your thumb. There's your thumb. And you would see your fingers. There's your wrist. I'll put your wrist first. And the rest of your fingers would grip into like that. So there's all your fingers there. Okay. Here's your thumbnail. There's your palm. This is the back of your hand. And therefore your grip rule is saying that these circles should go, in this case, anti-clockwise. Okay. So the grip rule is the easiest way to determine which way this circular pattern goes. Don't forget though that I'll just draw these things a little bit more correctly, that the closer you are to the wire, the stronger the field is. So the circles should be closer in, together as you go in, and then they get further and further apart. So this is as you go further and further out, get further away. Okay. Let's try and draw the magnetic field around this straight conductor here going straight down. So looking at this one now, so I'll just put this one away. So this time we're going to put our thumb pointing down. So don't forget, we always use our right hand. So if our thumb is pointing down, here's the thumb, our fingers would be curving away and into the board. So this would be the back of your hand that I'm trying to draw here. So there's the back of your hand and there's your wrist. Okay, so you wouldn't be able to see those ones there. Okay, and this would be the back of your hand and there will be your thumb. So I would be down there. And so we would be curling in, they're going into the board on this side. Remember, X's mean we're going into the board, and that each of these here is a circle going in, so there will be a circle coming out on the other side. So this is a circle going in here, this is the circle coming out, circular field line here, coming out here, in here, out here, in here, out here. The next one we will draw, be slightly further away. Okay, and for every circle that goes in, there will be an identical one going out here. I'm only using the same colours now to, the first one was yellow for no reason. They're all meant to be the same. And then this one here would be further away again. So the distances would be slightly further away because these circles are getting further apart. And for every one on that side, there will be a dot on this side. Okay. If you were to be looking up here, oops, there's our eye, and we're looking in, then you would see the current coming towards you. So you would see here is the current and that one there. And you would see circles going this way around that way. So you'd see circles 1, 2, and then 3. And once again, getting further and further apart. Now the strength of the magnetic field, so these are B, these are all lines of B. Okay, the strength of that magnetic field is given by Amperes Law. Oops, going the wrong way. So this is your first example that you will be doing in set a few more moments. Here is our current. Okay, we're going this way. And you are asked here to the direction of the magnetic field. In other words, is it going into the board or out of the board? Now, take a few moments to have a look at A. So this one here. Okay, align your thumb going this way. So your thumb is pointing that way. Okay. Which way do your fingers, just in your right hand, but don't forget it's the right hand grip rule. When your fingers are relaxed, they will look like this, and then your palm will be towards you there. So this means that the magnetic field will be coming out of the board at this point, so it would be a dot, and then it will be going in over here. So it will be coming out, circle, half circle, semicircle, into here, into the board, and it completes the circle. Okay? That means that if it's going out of the board on this side, then it has to be out of the board also on this side and this side. So B and C would also be going out of the board and into the board in here. So D would be an X, and it would reappear in this position. So D would reappear over there. So take a few moments, pause this video, and see if you can do the next part of 1. So looking at F, E, G, and H, and then going through to K. And then once you've done that, unpause the video, and we'll go through and having a look at the next part of question 1. So just question 1, A through to K and L at the moment. Just pause. Okay, welcome back. We're now going to have a look at what is around conductors which are falling in and out of the board. Not falling, but just moving out, in and out of the board. So this would be a wire that is looking end on. Remember, a wire is a very small, thin cylinder, very long, and this is the current. So this time, this is representing current. This is representing the edge of the wire. And the current is coming out of the board here. Using your right-hand grip rule, as we've been doing before, the magnetic field, once again, around a current conductor, it's circular, and I've been drawing them badly because you should realize that those circles are getting further and further apart. So if I undo those, so the next one would be here, and then the next one further away, and then the next one would be even further away again. So these circles, however, have a direction. Now, there's really no north and south here because it's a circle. It's just the direction of the magnetic field. And in this case, here, using the right-hand grip rule, if your thumb points out and relax your fingers, you will have them going in this direction here. So it normally would be going, if you're saying it's going from a north pole to a south pole, there is no start and stop. These lines are circles. They are closed, therefore there is always just direction to these circles. So we can't say there is a north pole or a south pole around this wire. It is just the direction is in this case, the clockwise, anti-clockwise direction. Okay, let's pause the video now and have a look at doing N through to W, and then come back. Right, now welcome back. We're actually going to do the mathematics now of Amperes Law. The first example that you have there is in question 2, 2A. You have a point P up here, and it is 8 centimeters from a current carrying conductor. Now the distance from P to the current carrying conductor is always the perpendicular distance. And the current is 2.5 amps. So simply, popping those values into Amperes Law, we get B equaling mu0 I on 2 pi r. And the only difficulty in this case here was just realizing that r is not in, has to be in meters, not in centimeters. And have base, which is 1.257 by 10 to the minus 6, times the current is 2.5, all over 2 pi times 0.08. Okay? That will work. Okay, and that gives us a value of 6.25 by 10 to the minus 6 Tesla. Okay, don't forget that the units of magnetic field are Tesla. It's a very simple formula to use and complete all of question 2 in set 76. When you're ready, come back to the video. Okay, this is question 3. You've attempted questions 1 and 2. This is a little bit of a complicated question, so I'm going to help you go through the solution. If you have a look at it, it's 4 current carrying conductors are shown in a square here. And we want to find, with the data that's given at each of the corners here, we want to find the total or the sum magnetic field right in the center. So in this position right there. Okay. So what we need to do firstly is we're going to just assume that there is only one conductor. So we're going to pretend that these 3 conductors just do not exist. So we need to find the distance that we are to the center. Now this distance here will be the same to all the other conductors. So once we've found that, we'll have no problem. Now we also know that if I was to create a right angled triangle here, that is a right angle there, and this would be the hypotenuse, which is 10 centimeters. So I want you now to use Pythagoras' theorem, and we're going to be saying that this is r using r in our formula, then r squared plus r squared would equal 10 squared. This is in centimeters, of course. So 2r squared would equal 100. If you can calculate what r is there in terms of centimeters. If we do that, we'll get that it's root 50 centimeters, which is approximately 7.07 centimeters. We'll leave it at that level of accuracy there. Okay, now we are just going to, I'll just rub those parts out. We're going to apply Amperes Law now, that B equals mu naught I on 2 pi, and we've now got our R, and our I here will be found from this one here. Remember, we were ignoring the other conductors. We're pretending that they don't exist. We just want to find the magnetic field strength in the center here. I'll try and make that a star so it doesn't look like it's in or out of the page, just because of this single conductor here. So by putting in 4 into that position and putting in root 50, or 0.0707, because it's got to be in centimeters, it's got to be in meters. Could you now pause the video for a few moments and calculate what is B due to this single conductor up there in the corner? Right, you've now paused the video, you've had a go at doing that. So let's just check, mark your work. We've got that the permeability of free space is 1.257 by 10 to the minus 6. The current was 4, all over 2 pi times 0.0707. And when that's calculated, it becomes 1.13 approximately by 10 to the minus 5 Tesla. So we've now found that the B at this centre here, due to this single conductor, is equal to this. Now this only tells us the magnitude, doesn't tell us the direction. The direction is going to be the hard part because we want to find the magnitude and the direction at the end. So the magnitude is going to be simply the additions of, well actually it's not going to be the simple additions, but we're going to have to add these as vectors very soon. So if you can pause the video now for a few moments, I want you to find the magnetic field strength due to the 2 amp one here. So now you're going to pretend that all of these ones don't exist and it's just between here and here. Okay, take a few moments now and pause the video and calculate that other one for us. Okay, you've had a few moments now to do that, and here's the working over here for the field strength. And when you do calculate that, it gets to be probably 5.7 by 10 to the minus 6 Tesla. In a few more moments, we're going to have to be able to add these two values together and use them, so we might have to express this at the same level of the exponent, but we'll leave that for a few more moments. Right, now we've done this one and this one, we have a look at the last two, and we notice that the combinations are identical. So this one here is 2 amps, and so is that 2 amps. So this one here will have the same as this one. So the field strength from this one here, the magnitude would be in the center, remember it's in the center here that we're talking about, would be 5.7 by 10 to the minus 6 Tesla. And this one over here is going to be the same as this one, which is 1.13 by 10 to the minus 5 Tesla. Okay, so we've got just these two values repeated twice. Now, we have to add them in the center. This is the harder part because the magnetic field strength is a vector, and it's going to be have to be worked out as the direction of a circle. So I'm going to clear off these values for a few moments. So you can have clearing those values off. And looking at the slightly smaller, putting that in there. This is the circular field around this conductor here, and here is the center point here. Now, using your right hand grip rule, that's the thumb is placed in the direction of the current. Now the current is here into the board, so you need to point your thumb into the screen and then let your fingers wrap, and you should get that the direction of the magnetic field is in the clockwise direction. So looking at what is happening right here in the center, there is this direction at that point. So we know that the field is at a tangent at this point. It's going to be 1.13 by 10 to the minus 5 Tesla, and it's going to point that way. So far we know that we have one pointing there from that one there. Now rubbing that one out, I'll write that all down, put that away. Moving this one over here now to this direction. I'll just get a little bit more circles. Okay. This one here is a around the 2 amp. It's pointing out. So your thumb is pointing out of the board, and when you do that, your fingers will relax into this direction. So at this point here, there's the center. Using the tangent at that point, then there would be a field vector there. So this one here is that direction. With the last one, I'll just put both of them on together. I'll just control copy that. Try to get them to look a bit overlappy there. At that point in the center, we know from our circular geometry that these two tangents would be at 90 degrees to each other at this point. Okay, so we are quite confident that we can easily add these two values later on as a vector. Okay, now just move that away. Oops, grab the right thing this time. Going down to this one here and try to work out what it's doing at the centre. I'll just make it slightly bigger so it does run through the centre. Okay, slightly wonky now, but who cares? Rubbing that out using our right-hand grip rule. That's our thumb is pointing now into the centre of the board. When it does that, you should be getting a magnetic field that is in the clockwise direction. So therefore, in the centre here, we would have one that's pointing this way. So this one here is going to be that one there. Okay. And similarly, if you can take a few more moments to now just pause the video and see what you would find if you put the circle around this one here. Just pause the video for 5 seconds and see if you can determine what direction it would do. Okay, welcome back. Now, what you should have discovered is that with this one down here, we have the current coming out of the board. So if it's coming out of the board, we would have it in this direction. And that means that, let's choose another colour, that at this point here, you'd have a tangent going that way. So we're going to go that way as well. So we now have the four directions of the magnetic field at that point. So let's just rub them away. So the red one, this red one here, that red one is the magnetic field that comes from that. And we know that that was 1.13 by 10 to the minus 6. The blue one here is coming from this one, and that is also 1.13 by 10 to the minus 6. And the pink one up here, this one here, is coming from this one, and the orange one is coming from that one, and they were both exactly the same. So that one there is 5.7 by 10 to the minus, oh, these were 5s, I think, sorry, my fault. That's 10 to the minus 5, 10 minus 5, and this is 10 to the minus 6, and this is 5.7 by 10 to the minus 6. So looking at that and just drawing this as a vector diagram, just get a bit of vector diagram, get some lines up with some arrows. We have one vector which is pointing in this direction at the centre, which is twice the length of this, so that's this one here. So that's going to be 2.26 by 10 to the minus 5. And we also have another vector which is pointing, I might make it into red here, this way out there like that. And we know that one's at right angles, and that value there is twice that, so that's 1.13 by 10 to the minus 6. Okay, I think I've got that right. No, it's 10 to the minus 5. No, it's not. That's just go to pause the video, and I'm just going to check that I've added those correctly up. Okay, I have added them up. I just got the wrong indice at the top here. So that should be a 5. Okay. Now to add two vectors together, we've got to make sure that we put them head to tail. So I'm going to move that one down here. And our final vector, our resultant vector, will be used from the beginning. I'll do that in a light blue. From this position down to here. It's going to be a slight angle. Okay. And when we do that, we can find this angle in here in a few more moments for its value. So take a few moments to find the resultant vector r here by using Pythagoras' theorem. Don't forget these two are at right angles. We are at right angles here and we're at right angles there. So take a few moments to pause and find that. And also, could you use trigonometry to find this angle up here? Okay, just take a moment to pause the video and find those two values. Okay, just check your results here that we have using Pythagoras' theorem that this resultant vector down here is 2.53 by 10 to the minus 5 Tesla, and this angle up here using tan would be this value over that, shift tan, and you get 27 degrees. It's actually 26.5, but we'll just go with 27 for mental calculation. Right, so we now know the magnitude. The hard part will be now determining this direction. And the thing that we've got to remember is that this line here, if we put these back in here, that line there that we've just drawn here is this line here, and this is 45 degrees. And we now have this as 27 degrees here, so we can now calculate the true bearing all the way across to there. Okay, so take a few moments just to write the true bearing, or you could, if you would like to, this is south and that is west, you could determine the south towards west notation if you'd like. But let's just try the true bearing. Pause the video now and check what your bearing is. Okay, well, I got that this was a bearing of 198 degrees. The way I did that, adding these two together, oops, put that back, adding these two values together, we got 72 degrees. So if that's 72 degrees, we can work out all the ways 270, subtract 72, we get 198. So the total value would be, it's 2.53 by 10 to the minus 5 Tesla at a bearing of 198 degrees true. Okay. You're going to now complete question 4 and 5. Now 4 is, all of those are exactly the same, so please realise the hardest part will be to work out how they're going to happen. So have a look at the solutions. You'll see that because they're all tangents, you'll have the three things in three directions. Question 5, and then you're going to question 7. So if you could do 4, 5, and 7 now. Okay, thank you very much.